Namaste dosto. Imagine you're drawing the simplest path from one point to another. What do you get? A straight line, right? It's the simplest and most fundamental object in coordinate geometry. But did you know a straight line actually represents a special set of points that satisfy an equation? Yes, in two-dimensional geometry, a line is made up of infinitely many points, each with coordinates x and y that all satisfies certain linear equation. This general equation looks like capital A times x plus capital B times y plus capital C equals 0, where A, B, and C are just real numbers. For example, if you plug in values of x and y that satisfy this equation, those points will fall exactly on the line. Now, lines can wear many faces or forms: slope-intercept, point-slope, two-point, and normal forms, each useful depending on what information we have. Straight lines are super important because they form the backbone of solving geometric and algebraic problems. And trust me, they pop up everywhere, from calculus to vector algebra. So keep your eyes on the coordinate plane where lines of different types stretch in all directions: horizontal, vertical, or slanted. Arey wah! It's like the language of algebra meets geometry right here on this plane. Now, let's step a little deeper. What is a line? Actually, in analytic geometry, we think of a line as a locus, meaning the set of all points that satisfy a certain condition. Imagine a magician's wand pointing to every point that fits one simple rule. Together, those points trace out a line. When the condition binding x and y is linear, like y equals mx plus c, the locus is a straight line. For example, all points satisfying x plus y equals 5 lie neatly along a line slanting across the coordinate plane. This idea lets us turn geometric shapes into algebraic equations. Whether it's a line, a circle, or a curve, the locus concept is like a bridge joining geometry and algebra. It makes analysis and proofs much easier. So next time you see a line on a graph, remember, it's really the path of all points obeying one simple, elegant rule. Let's talk about the most general way to write a line's equation: ax plus by plus c equals 0. Here, a and b can't both be 0. Otherwise, it won't represent a line at all. This general form is very powerful. Depending on the values of a, b, and c, the line can be slanting, horizontal, or vertical. For example, if b equals 0, the equation reduces to ax plus c equals 0, or simply x equals minus c divided by a. That's a vertical line parallel to the y-axis. On the other hand, if a equals 0, the equation becomes by plus c equals 0, or y equals minus c divided by b, which is a horizontal line parallel to the x-axis. So this one equation, ax plus by plus c equals 0, cleverly covers all types of lines. Isn't it fascinating that by tuning the constants a, b, and c, we can control both the direction and the position of the line on the plane? अब बात करते हैं slope की. The slope, usually written as m, tells us how steep a line is, or in simple words, how much it tilts compared to the positive x-axis. Imagine a ladder leaning against a wall. The angle of inclination, called theta, relates to slope as m equals tan theta. So if the ladder is steeper, theta is bigger, and so is the slope. Now, if you know any 2 points on the line, say coordinates x1, y1 and x2, y2, then slope can be calculated using m equals y2 minus y1 divided by x2 minus x1. Let's say that again slowly. Slope equals the change in y divided by the change in x. This tells us how much the line rises or falls as we move from left to right. Two lines are parallel if they have the same slope, meaning they tilt at the same angle and never meet. And perpendicular lines? Their slopes multiply to minus 1. That means m1 times m2 equals minus 1. It's like two friends meeting exactly at a right angle. There are many ways to write the equation of a line, each with its own special use. First, the slope-intercept form, y equals mx plus c. Here, m is the slope and C is the y-intercept, or the point where the line crosses the y-axis. Next, the point slope form y minus y1 equals m times x minus x1. This is handy when you know one point and a slope. Then comes the two-point form y minus y1 equals y2 minus y1 divided by x2 minus x1 times x minus x1. This directly connects 2 points on the line. We also have the intercept form x divided by a plus y divided by b equals 1. Here, a is the x-intercept and b is the y-intercept. And finally, the normal form x cos alpha plus y sin alpha equals p. This uses the perpendicular distance p from the origin and angle alpha made with the x-axis. Let's revisit the slope relations that tell us if two lines are parallel or perpendicular. If slopes are m1 and m2, then lines are parallel when m1 equals m2. Lines are perpendicular when m1 multiplied by m2 equals minus 1. For example, if slope 1 is 2, slope 2 must be negative 1/2 for the lines to meet at a right angle. These simple slope rules help us quickly check if shapes like triangles or rectangles are right-angled, or if tangents to curves are perpendicular or parallel. Time for an example. Suppose a line passes through the point with coordinates to -3 and has slope m equals 4. Let's find its equation. We use the point slope form y minus y1 equals m times x minus x1. So, plugging in values, y minus -3 equals 4 times x minus 2. That simplifies to y plus 3 equals 4x minus 8. Rearranging, we get y equals 4x minus 11. This is the final equation. Quick check. If x equals 2, then y equals 4 times to minus 11. That is 8 minus 11 equals -3. Perfect. It passes through the given point. Let's quickly recap what we've learned. Formula 1. General form of a line. Ax plus by plus c equals 0. Formula 2. Slope between 2 points m equals y2 minus y1 divided by x2 minus x1. Formula 3. Point slope form y minus y1 equals m times x minus x1. Remember, a straight line is the locus of points satisfying a linear equation. The slope tells us its tilt. Parallel lines share the same slope, while perpendicular lines have slopes that multiply to -1. And the big idea, visualizing lines on the coordinate plane connects algebra with geometry. Every equation is like a picture waiting to be drawn. Now, here's a quick challenge for you. If a line passes through the point 1, 2 and has slope -3, can you write its equation using point slope form?